competency in utilization of the natural resources. So when we talk about natural resources, we will talk about element of soil, water, air, and even organisms. So organism basically includes plant, animals, microorganisms, organic materials, the living being in or on top of the soil. So since my expertise, as Dr. Roselli pointed out, is more on soil physics, so basically I will focus today on soil and water. So I want to talk about how we can actually utilize the water in a more what I call efficient way. It means we want to use less, but to achieve the same outcome. All right. So you might ask, if there is a soil physics, could there be any other field? The field that when you're in school, you learn about physics, chemistry, biology. So the answer is yes. So we have soil, not just soil physics, we have soil biology, and also soil chemistry. And then you might ask this question: how come you have this kind of agriculture engineering, things like that, like environmental engineering, civil engineering, mechanical engineering? So these fields are actually a more later. I mean, we call it's a subsequent field that developed. So if you look back into the civilizations of a human being, we start our civilization by developing agriculture. Okay, so we need to have a good agricultural activity that can continuously produce food. So that's where the basic element of discovery, management, actually happening in a very old time. So in terms of agriculture, relating to soil is actually a very, very old science. So eventually people feel that, okay, not just agriculture, we need to include the elements of economics, elements of social, economic, the elements of what I call reducing pollution, things like that. So that's why we have this environmental technology, environmental engineering course, and then civil, of course, then other courses as well. And then this is how this is why the science from agriculture is a very, very old science. That's why they have a very long history of development. So once you dig deeper into the science in the agriculture, you eventually came across soil chemistry, soil biology, and soil physics. All right. So today, the talk I want to focus more on soil and water. And when we talk about water, I want to talk about the efficient way of using water. We want to use less water, as I mentioned, but yet we want to still maintain to achieve the same outcome in terms of productions. So there are a few reasons why we want to reduce the consumption of water, because you see, if you look into the agricultural field, I mean, you might working on something like hydroponic, things like that, more controlled environment. That is a different story. But if you look at the large scales of agriculture, they're using the land basically for mass productions of plants, of these vegetable, fruits, things like that. So when it comes to big scales, you are using a lot of organic materials. You might place some fertilizers, not just fertilizers. You might also use a pesticide, herbicide, and you also need to provide water into the plantation land area. So if you provide too much water into the site, so first of all, you're going to waste money because you're providing too much. So you might deplete your resources faster. Second, if you provide too much water, and it will dissolve your organics, the nutrients you provide to the soil. It would also dissolve the pesticide and herbicide. So what happens is that this solute that dissolve in the water will be carried into the underground. So what does it mean? That means that your groundwater will have high content of nutrient. Okay, these nitrogen, phosphorus element, and then you also contain this pesticide herbicide. So your groundwater will be heavily polluted. So imagine that you have a nearby river. So this groundwater will eventually flow into a river, then pollute the water resources, and that's how you will get a lot of problems. Like rivers has this algae, this changing in colors. The water is polluted, things like that. So efficient use of water is not just to reduce cost, but it actually helps to reduce environmental problem at the later part of human activity. So you could save the river eventually. You could also save the groundwater, not just save the money. So let us uh, look into this picture. Then let us just focus on the consumption of water. So you have a piece of land, soil, and then you plant something on top of it, and then you, one day or not, you're going to provide water. So the natural way of getting water is from rainfall. So obviously, rainfall is not a good way to maintain your plantation. So you have to provide irrigation because you want your plant continuously to grow and produce fruits, produce vegetable. Okay, so you have to provide water. So imagine that you provide water and you start to see that water start to infiltrate into the ground, and then you thought that okay, not enough water, we have to produce, you have to provide more water. So up to a stage that you see that there's a standing water, or in other words called ponding of water on top of the soil. So at this stage you could say that the water can no longer penetrate. So you could also imagine that the pores in the soil is actually filled with water, so fully filled with water. So if you leave the water, if you stop providing water, then you can see that the standing water start to drop. Okay, and then the soil will start to dry. Right, so you can see that happen in front of your eye quite quick. So for example, if the soil is actually made up of lots of sand material, so you can see the water drop very fast. But if the soil material is made up a lot of clay, then the drop of water will be very, very slow. But in any way that if you can see that water start to drop, and then of course this is one of the physics in play. So the water that's draining very fast into the soil, into the soil, the physics in play is actually the gravitational force. So the gravity actually pull down the water very, very fast, and this is the process what we call draining. Okay, so the water actually drain through the soil, and the draining happen because of the gravitational pull. So the gravitational pull take out the water from the soil, and then you can see the soil become drier. So so when first the water start to drain, when the ponding water start to dry, so the ponding water level start to become at the same level as the soil surface. And this is the stage where you get something like we call zero pressure. Okay, it's also good for me to explain a bit about zero pressure, but we talk about that later on. But when the water drop further from the surface of the soil into the soil, then you start to get this kind of negative pressure. Okay, negative pressure. So imagine that you have a plant or tree, okay, or vegetable grow on top of the soil. So the plant or tree, they absorb the water, right? So you might ask, what kind of pressure is used to absorb the water from the soil into the plant? So the pressure that they absorb the water is actually called suction. They call it negative pressure. So the plant or tree absorb water from the soil, they actually suck the water up from the soil. And the pressure is in the form of negative pressure. So actually there's a sensor, we can actually put it in the soil and measure what is the pressure in terms of negative value, how much is the pressure, right? So we can actually do that. So when the water actually drain from the soil, all the water that left in the soil is actually being pulled or sucked by the soil, and then the pressure exists, the water pressure that exists in the soil is actually in the forms of negative pressure. All right. So back to the discussion where we talk about the water drain from the soil because of gravitational pull. All right. So after that, the water left in the soil is attached by the soil, is attracted by the soil. So that stage is what we call field capacity. So the water that can be captured by the soil, be sucked by being attracted by the soil, that is called field capacity. So this water that attached to the soil, how do we know? If you let the water drain through the soil, then you use your hand to grab the soil, and you can feel the moist left in the soil. That is the field capacity. That's how much the soil can actually keep the water without being pulled out by the effects of gravity. So this water available in the soil is available to the plant root. So you have a vegetable, you have trees, everything, fruit trees. So they're absorbing water. So this water that leftover after draining is available for plant root absorption. So plant root will continue to extract this field capacity moisture content from the soil up to a level where they can no longer pull, because you see water they do not discriminate, so it goes to whoever pull it with the highest pressure. So the plant root will actually suck the water up from the soil at a negative pressure. The soil also pull the water with a negative pressure. So if the plant root extract the water at the greater pressure, so the water will move into the root and will be used up by the root. So as the plant root continue to drain the water from the soil, the water left over in the soil becoming lesser and lesser and lesser and lesser, up to a stage the attractions of the water towards the soil, or the soil attractions towards the water, is very, very high. Means the negative pressure is very, very high. That is the stage where the plant root can no longer extract the water that's left over in the soil. This is the stage where we call the permanent wilting point. Permanent wilting point is, you see the word wilting. Wilting means in Bahasa Malaysia we call it down Melayu. Okay, it start to become not something not crumble but wilting. So it start to dry, it start to like become smaller in size, So they like folding up together, something like that. So that is called wilting point. Why is that happen to the plant leaf? Because the plant leaf can no longer extract the water from the soil. So the leaf, because the leaf stomata is open for exchange and evaporation of water from the surface. So there's no longer enough water left in the leaf. So the leaf start to wilt. That's what we call wilting point. It also because the water available in the sand in the soil is not enough for the plant root absorption. Right. So if we look deeper into this process, basically we can separate into three stages. We have the saturation, okay, when the soil is fully saturated with water, and then this soil can be drained because of gravitational pull. So the water left behind is what we call field capacity, and then the field capacity can still be absorbed by the plant root. So the water will continue to decline because of the plant root absorption. And then we reach a stage where we call permanent wilting point. So the amount of water left in the soil at permanent wilting point is not available for plant root absorption. So then, of course, you might ask, since we're in plantation, so our concern is the water that left between field capacity and permanent wilting point. So the water that store from field capacity to permanent wilting point, these are the water that available for plant root absorption. And then you might ask why the saturation water is not good for the plant. The saturation water is also good for the plant. It's just that the water doesn't stay in the soil that long. So after you saturate the soil, the water in the soil will quickly drain out because of gravity. So this water stay there maybe less than half an hour, maybe 1 hour, and then you have 24 hours a day. So the gravitational pull will simply just take out the water very fast. So this water most of the time not available for plant root absorption. So that's why when it comes to soil agricultural land management, the plant water available, or PAW, is the water that we should focus on, because these are the mostly available water for plant root absorption. So we need to find out what's the field we need to find out the soil moisture content at field capacity, and we also need to find out the soil moisture content at permanent wilting point. So you can see that at saturation, the pressure P, I think I put the symbol P here, equals to 0. At field capacity, is less than 0. At permanent wilting point, is very, very less than 0. So it's very, very negative. So you can imagine that field capacity is negative pressure. Permanent wilting point is very negative pressure. So it's very low pressure. All right. So and that is a value here we can provide to estimate the soil moisture content. We can actually do that by using the characteristic curve, or we call it water retention curve. Okay. So the normal way of knowing the amount of water in the soil is to conduct laboratory measurements. Okay, and this will be a conventional way. But nowadays, technology has progressed so good that they can actually measure the soil moisture content using sensors. So the one that we always see, in a system like Arduino, they use this kind of resistivity sensors. Those are a good indicator, but it's not the one that you would see in a commercial market, because resistivity, the one that used in Arduino, is not that high end. Okay, it's not that accurate to be exact. So a more accurate one, they are going towards like capacity sensors. The most accurate available in the market now is time domain refractometry, or in short form we call it TDR. So yeah, so TDR is the best technology available. Sometimes you want, if your sensor can cost you about maybe 5-10,000 to get that sensors for you to do measurement. The higher end than Arduino, the easily you can get is like 1 to 2,000 ringgit to measure soil moisture content. Those are more accurate. So the difference is that you use resistivity, they can only sense when the prod you push in the soil in touch with the water. But when it comes to sensors like capacity and TDR, is that they can sense the soil volume. So how to say, it's like like a magnetic field. Okay, like a magnetic field, you can sense the field before you touch the surface. So if their sensing volume is actually bigger. So that's why their measurement of soil moisture content is actually more accurate. But of course, they need to do some kind of calibration. So laboratory method is very accurate. Nobody can deny, if you use laboratory method, it's very accurate. But this is a time-consuming process. Imagine that you have hundreds of samples, maybe perhaps thousands of samples you need to manage. Take for example, there's one time I went to a DOA meeting at Putrajaya. They were asking me, is there any sensors to actually measure the soil bulk density? And because they have hundreds of samples to measure soil bulk density, and they don't have enough instrument to actually measure that value. Even they have the instrument to do that kind of thing, it's not practical to measure so much samples in a very short time. So they're looking for commercial instrumentation to do the measurement. So because of this, that's why sensors are becoming more important nowadays, because we're going to get more information in a short time. So laboratory method is always the best, but sometimes we are being constrained by the number of samples that we can deal with. So on-site sensors is a current approach that we use, or an instrument in the field, in the laboratory. Even just put in the sensor, give you the value straight away. So that is good, because we have a data collection that is quite rapid, means a fast collection of data. But keep in mind, this method is expensive. Okay, you need to pay a lot of money to get that kind of instrument, and of course calibration is needed. So if your calibration is wrong, so all your measurement is also wrong. So you need to do a proper calibration. So you might ask, if I want to know about the water in the soil, is there any other way, any easier way? That is, we call it early site assessment. Not we call it, just I name it as early site assessment, or in short, you call it screening tools. So you can actually screen the soil even before you go to the site. How do we do that? You take the information from DOA, Department of Agriculture. They give you the information, tell you this place is what kind of soil, that place is what kind of soil. So you know the soil type, and then you will know the soil textures, and then you can actually infer the information regarding the soil. So today I'm going to show you how this is being done. Okay, so one might ask what to do when the soil is dry. So it's very simple. You just supply water through irrigation system, and the question arises when to irrigate the soil. Okay, so you just supply water until what, and then another question is, you supply water until what level of soil wetness is considered enough without causing unnecessary water wastage. As I mentioned just now, if you saturate your soil, you basically is going to waste the water, because why? The water is going to flow into the groundwater. It's going to suck. It's going to be drained out from the soil very quickly because of gravitational pull. So you don't want to supply the water up to saturation, because it's going to be wastage, right? And then furthermore, your plant root is going to be hurt, because it's too wet all the time, right? So we don't want that to happen. So we want to provide the water. We want to provide the water also in the sense that we don't want to waste the water. And because you also know that providing too much water will also dissolve the organics nutrients, the pesticide, herbicide, and carry all the way down to groundwater and then eventually to the river stream. And then to answer this, we need to know the soil type, okay, that we are dealing with. So you want to develop a land, you must at least know the soil type. How do you know? You just get the information from the DOA, Department of Agriculture. Okay, so and then we could conduct early site assessment. Okay, so to conduct early site assessment, if we only know the soil type, soil textures, so there must be a way that we can actually relate the soil textures with the soil moisture content. Otherwise, having a soil texture is not that useful. Fortunately, there is a method to actually do that. We call it this pedal transfer method, pedal transfer function, something like that. So can we relate soil type with to soil water content? The answer is yes, we can actually do that. And you can see there's a graph here. So this graph here is showing to you this water retention curve or the water characteristic curve. So basically you have a soil moisture content, soil water content. So you can see that the unit is meter cube over meter cube. So it's basically referring to the meter cube of water over the meter cube of soil. I mean the volume of soil. So this is what it means. So for example, you see here you have 0.2. So it's like 20% is actually fill out with this water content. Right. So then here we have this soil metric suction. I can see there's a negative centimeter. It can be negative meter, but the negative is just to show you that it's a suction, it's a negative pressure. Okay. All right. And then we have two lines. So one line is referring to the field capacity, and then the other line is referring to the permanent melting point. So because we can actually relate field capacity and a permanent melting point to a specific to their specific pressure. Okay, and we are going to talk about this now. So early site assessment method is to rely on soil textures. So from the soil textures, we can actually determine the soil hydraulic properties, such as the soil water retention. Also, this graph is actually the soil water retention, as I mentioned. So you have a soil water content versus the soil metric suction, which is the negative pressure, right? And it is common to assume that the field capacity and the permanent melting point correspond to a specific soil suction pressure. For example, this field capacity, soil moisture content or soil water content at this will be determined at negative 330 centimeter. Okay, 330 centimeter water suction head. So here, 330 is somewhere here. So we can draw a line vertically and then draw a line horizontally. Then we could determine the field capacity, soil moisture content. And then for permanent melting point, we determine it at 15,000 centimeter. So 15,000 centimeter is somewhere here. So we draw a line up vertically and then horizontally, and we can determine the permanent melting point, soil moisture content. So from there, we get the field capacity, soil moisture content, as well as the permanent melting point, soil moisture content. And this line corresponds to silty clay loam. So silty clay loam is one of the soil structures. We soil type. You can also have a different like sand, clay, loamy sand. So we have a different type of soil textures. All right. So this is an example. So I only show you the silty clay. All right. So if we take the difference between this value, field capacity, soil moisture content, minus the permanent melting point, soil moisture content, we are going to get the PAW. So the plant available water. This is how we get the plant available water. And basically, this plant available water is referring to the amount of water available to plant root absorption. So the plant root can actually take out the water. And this is how we actually do that. Okay. So even though we have this information, plant root available water seems like good information, but to a person, to a manager that managing a site for plantation, this is not quite useful, because when it comes to site management, we need to know how much water we need to provide, and with this amount of water, how long we need to supply. We need to like dump it all on the surface at once, or with this amount of water, we will spread it out over time for how long, right? And then even we irrigate the soil. For example, you're doing your planting vegetable. Your plant root is not very deep, right? Plant root is not very deep. So there's only certain depths of soil that you're interested to get it wet. Other than that, no, you're not interested, right? So you must know how much water you need to provide and for how long, and at what deep that you expect the water to get to, so that it could reach the depths of the plant root, and so the plant root can actually take the water out of it. That's why you know that nowadays we have this kind of what you call this dripping irrigation. Yeah, dripping irrigation. So the reason of having a dripping irrigation is just what, to save water. It's intended to save water, not to waste water, right? So 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 you have to adjust your dripping water correctly in that sense. So this is exactly what we're trying to point out. So you need to provide just enough water, not too much water. That's why we need to, after we know the plant available water, we need to do one more step further. We want to know how long will the water get into the soil, how much we need to provide, and we need to provide that amount of water for how long in the time we need to provide the water. Let's say you want to provide 1 liter of water to the pot of soil, then you want to pour that 1 liter of water right away, or you want to spread out the 1 liter of water over time, over a few hours. That is the kind of question that we're asking. So if you know the volume you want to provide, and you know the time you want to provide that amount of volume of water, then you can actually determine the rate of providing the water. So you take the volume divided by the time, then you get the rate of water irrigation rate of water. Okay. So to demonstrate what I just talked to you just now, and it's good for me to show you an example. So we are going to we use a case study on a Terengganu soil to demonstrate the method we have just described. All right. So the research aim objective as following. So the current study aims to establish an early site assessment procedure to evaluate soil series. In this case, it's Terengganu. Okay. So regarding the plantation water supply. And then the objective of study is as follows. So we have first we need to classify soil series, Terengganu soil, for example, into soil textures. So we know the soil series, and we need to convert it into a soil textures. And then from the soil textures, we can actually infer the soil hydraulic properties by using pedal transfer method. And then the third objective is to determine the field capacity, the permanent wetting point, and the plant available water. So I already demonstrate to you the method that how we actually can do that. And then the fourth step, which is to conduct water infiltration at field capacity into different soil textures. So this one I haven't discussed with you yet, but you see that we're going to infiltrate the water into the soil at field capacity. So we are actually interested to know how much water we supply that's enough, but not too much until it's drained. So the water can actually stay in the soil and available for the plant absorption. So hence the methodology is simply to identify the soil series for Terengganu states. And then second, to determine the soil textures. So that's basically based on the percentage of sand, silt, and clay. And then third, to identify the soil with water retention function. And then this one you can easily achieve it by using pedal transfer method. And number four, we estimate the field capacity, permanent wetting point, and plant available water. And the last part, of course, to conduct water infiltration study. This study only show you the single flow regime at field capacity. Okay, and then of course this study neglect some others effect that, for example, evaporation. We are not talking. We do not include it here. Temperature variation. Okay, daily temperature variation. We do not include it here. Vapor flow, bulk density, soil heterogeneous. We also not included in this study. Okay. So there are some other things also not included, but this enough for our discussion here. Just to tell you that there are some other things that we're not going to touch, but it's also affecting the study. So objective one, we have a Terengganu soil series and the soil structure. So we now have this what we call we identify there are basically 12 soil series originated from Terengganu. So basically there are a lot more soils in Terengganu, but the soil soil series that we call originally found in Terengganu, we have 12 types. Okay, according to the Department of Agriculture. And then from this 12 soil series, we can basically classify into 5 soil textures. So you can see that in Terengganu soil series, we have a lot of clay soil textures, and then we have two soil series as sand, and one as loamy sand, and one as a silty clay loam, and one as a clay loam. Right? So we have lots of clay and a little bit of loamy sand, silty clay loam, and then clay loam. All right. So adjective 2, we will have to determine the water retention function. Sometimes it is also called water characteristic curve. Okay. So basically, it's a relationship between soil moisture content with soil metric suction. So you can see here we have for 5 different soil sections from clay loam to sand, clay, and then loamy sand. Okay. So one of the interesting things you can see here, if we determine the field capacity at negative 330 centimeter, and also the permanent wetting point at 15,000 centimeter. So you could see that for sand, okay, this line, this characteristic curve, this retention curve, is for sand. You can see that it's not much different. If you determine the field capacity, soil water content, and the permanent wetting point, soil water content, they are more or less the same. They are very close to each other, right? So if you look at clay is bigger, okay? So if you determine the soil moisture content at field capacity, and then the permanent wetting point for clay, so you can see that there's a larger difference for clay, uh, for clay soil, right? So among these 5 soil textures, obviously you can see that this dotted line, which is a silty clay loam, has the biggest difference, okay? Because the slope is actually the greatest among these 5 soil textures. So from here, you could actually expect that the plant available water given by soil silty clay loam will be the highest, right? So you expect to get the highest plant available water for silty clay loam, and then the smallest coming from the sand. So as what we expected, so we get the highest plant available water for silty clay loam, and then of course the smallest coming from the sand. So it turns out that silty clay loam can store the most water. So plant available water basically means how much water can actually store in the soil and available for plant root absorption. So silty clay loam turns out to be the best, okay, the most desirable, and that means it can store more water in the soil available for plant root absorption, and it means that less irrigation frequency is required. So you don't have to irrigate the soil that frequent because it can store more water. Whereas for soil, you see, it is less desirable. Why? Because frequently need irrigation. So you need to provide more water because the sand can store so little water. So if you try to plant in the sand, basically you're getting yourself into trouble unless the soil, unless the plant is actually like dry soil condition. Otherwise, planting in such a soil will only make you, it only give you a lot of headaches. It means you need to provide more water because the soil type, which is sand, it always dry, fast, and not enough for the plant to actually absorb the water from the soil. Right? So that is helpful in some sense. But this information is good to know, but not informative enough in helping managing water resources in plantation. As I mentioned to you, water management could actually benefit from the information such as time needed to irrigate the soil, how much time you need to irrigate. If you want to start your irrigation system, right, you want to start it for how long, okay? And then how deep the soil has to be infiltrated by water, because your plant root is different. So the reason you provide irrigation water is to irrigate the soil depth that you want to irrigate so that the plant root can actually absorb. So a certain depth of the soil that you're interested to get it wet, that's all right? And then how much water has infiltrated into the soil. That also means you need to prepare a reservoir where you extract the water from, you pump the water from. So you need to make sure that what is needed in the plantation is actually enough from the supply that you have. So otherwise, you need to do a proper planning, and you need to get the water from somewhere else, right? So therefore, water infiltration will be useful. So water infiltration study will be useful in this aspect. All right. So one question arises after knowing the PAW. This is just a repetition of what I just discussed with you. So we need to know how much water should we provide to the soil. We need to provide the water for how long? How deep will the water infiltrate into the soil? And at what rate the water should be supplied to the soil? So basically that translates into a numbers, into a numerical value that we can actually quantify. For example, we need to know the water volume, okay, V. We need to know the irrigation time, T. Means that if you turn on the hose, so the hose of the water has to be on for how long? So the irrigation time is what we're talking about. So the soil depth filled with water. So exactly how deep the water you want to, how deep the soil that you want to irrigate, and then of course that will actually translate into a water infiltration rate. So if you take the volume V divided by the time, then you get the water infiltration rate. So you know that you need to control the rate how you provide water to the uh, uh, land, okay, irrigation to the agricultural land. Right. So to answer this question, simulation has to be carried out for estimation based on water infiltration study using Richard equation. Okay. So this brings us to objective 4, so which is the water infiltration study. So this is a Richard equation. This is a PDE, a partial differential equation for governing water flow in unsaturated soil. So when you study about soil, maybe you might study about groundwater. So if you came across groundwater, you will talk about this Darcy's law. So Darcy's law is good to govern the water flow in saturated soil. Okay. So when it comes to unsaturated soil like agricultural land, if you agree with me, agricultural land is always partially filled with water, so they're not saturated. So the equation that we use to govern the water flow in the unsaturated soil is actually the Richard equation. So the Richard equation, you can see here, it has the water content, it has a diffusivity term, it has this hydraulic conductivity. So basically there are two mechanisms in play in this equation. Okay. First is the water diffusion. Okay, it's how the water actually diffuse in the soil. So basically, water is diffused from the high concentration to low concentration, high pressure to low pressure. That's how the water actually moves. And then there's a gravitational. That's why just now we talk about gravitational pull. So the water, if you put too much water into the soil, the water will be pulled up by the gravitational pull. So now you might ask a question: is it in a field capacity and a permanent melting point there's no gravitational pull? The answer is no. The answer is the answer is yes. We still have gravitational pull there, but it's not that strong. But at a stage where it's fully saturated, the gravitational pull is very, very strong, right? And then this equation cannot function alone. You see this, you have this diffusivity term and as well as the hydraulic conductivity term. So this is given by this Van Genisten constitutive functions. So there are many constitutive functions. Van Genisten is one of them, and it's the most well-known constitutive function that fit into a Richard equation. You can So uh, 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 finite difference, you might learn it in mathematics. So finite difference is the way that we use to solve the PDE, right? So the way that we use to solve the PDE is that we use the finite difference method to break the PDE into algebra. It means algebra, you study about algebra before, so you have a matrix, things like that. So when you break it into algebra, the algebra can be actually be being coded into a programming language. So in this case, I program it in a Fortran 2008 language. It's a very old language. You can use any language you like. For example, R nowadays. People also use other types of language. C++, C++ also another old language. Java perhaps, okay. So I use Fortran, so that's how I do it. Apart from finite difference method, there's other methods. For example, finite element method, finite volume method. So there's a lot of methods around, and the easiest one is actually finite difference method. So some people might focus on the this numerical method. For me, it's not so important because for me, the most important thing is to solve the problem, right? So that's why I just use finite difference. It's the oldest and the easiest method to use. So we actually in the objective 4 we conduct the water infiltration study at field capacity. So we are getting this soil moisture profile. So at here I show you two examples: sand and a silty clay loam. We know that sand is the less desirable, and the most desirable is silty clay loam. So you can see that this is the water infiltration. So you have the soil moisture versus the soil depth. Okay, so we can see that over time, at different time, the soil infiltration profile will be getting deeper and deeper into the soil, right? And both of them are infiltrated at field capacity, okay, at field capacity, right? That's why you see that the value of soil moisture content is different at field capacity for sand and also silty clay loam. And also the infiltration profile is also different. You can see that for sand is concave inward, whereas for silty clay loam, the soil moisture infiltration front is actually concave outward, right? And in this case, if you see there's four different water infiltration front at different time. I particularly choose a depth for discussion here. Let's say I choose a depth of 1.3 meter. Okay, this is 1.1, 1.2, 1.3 meter depth. So at 1.3 meter depth for sand, you need about 115 days for the water to actually reach this depth. So you might be shocked, say, how come it's so long? If when I provide the water, instantly the soil is wet. Remember that we're providing the water at the field capacity, so it's very very low soil water content, and we do that simply just to see how long for the water to get in. So if you look at silty clay loam, it needs about even longer, 478 days, like forever, okay, for the water to actually get into the soil. But once the water get into the soil, so only this amount of water will stay in the soil. That's why you see this water will, at field capacity can really stay in the soil for very, very long because it's very, very slow to get in. And that's why they stay there very, very long. So once they get into the soil, it's very slow to actually get away from the soil. So they stay there for very long because the gravitational pull is not that strong at that stage. All right. And so we can see here the water infiltration front shapes are different for different soil. And if we fix the soil depth, okay, we fix the soil depth, we could estimate the time to depth. So you can see the time to depth, and furthermore, you'll know how much water are actually entering the soil. Okay, how much water has entered the soil. So we can also estimate the water storage based on the area covered by the graph. Okay, so we can actually estimate the volume. So we have the volume, we have the time. So what can you do? You take the volume divided by the time, you get the rate. Okay, so we can estimate the infiltration rate, so which is given by V divided by the time T, right? So you get the rate. So, and then there's another thing we can do out of this information. We can actually plot another graph to show that, for example, just now we talked about 1.3, right? So now let's just talk about 1.2. Just at this example, I show 1.2. You can also talk about 1.3 meter deep. So let's do it at 1.2 meter deep. And this time also the same, we'll talk about sand as well as silty clay loam. So if you take an example here, 1.2, let's say we want to irrigate up to the depth of 1.2 meter depth. So you look here, and we draw a horizontal line and then a vertical line subsequently. We know that to get to 1.2 meter depth, we need about 100 days, okay, about 100 days. And then at the same time, we could predict the amount of water we need to provide. So you can get the amount of water, we can get the time. From there, we can actually estimate the rate of water supply to the site. Okay, the same thing goes for here, right? So you might be also interested in a depth of 0.65. All right, 0.65. You can determine, okay, maybe here is the like 20 days to get to 0.65 depth, and then you can also estimate the volume of water here. Okay, volume of water. So here I showed you the meter cube over meter square. Meter square is basically the area. So let's say your area is 1 acre. So you just just multiply with the area you have. Then you get the volume of water you need to provide. This is how simple it is. So why do we need a different depth? Because your plant roots depth is different. Okay, that's why we provide this graph that you can actually estimate for different depths that you are interested in. Basically means you refer to different root depth of your plant. So then, of course, we do that. We are actually interested to looking for soil type with the following properties. For example, we are interested in the shortest time and then the highest water storage. So we want to provide the water, and we want the water to get into the soil the fastest possible. And then we want the soil to actually store most of the water that we provide, right? So we compare the 5 soil textures overall. So you see that the water infiltration time. So the shortest time is actually given by sand. So sand, the water can actually get into the soil very, very fast, right? And the slowest one given by clay, right? And then for the water that's stored in the soil, so you can see that clay can actually store the most water, but when it comes to sand, it's almost none. Okay, it's near to zero, so it's not visible at all. So sand cannot store the water, even though the water can get into it very, very fast. So if you compare all these 5 soil textures, so it becomes apparent that the best soil textures when it comes to the perspective of water management, definitely it's going to be silty clay loam, right? So you have a second shortest time, okay? Sorry, I think it's not the second shortest time. It's one, two, three. It's the third shortest time, okay? Third shortest time, and then when it comes to water storage, it's the second largest water storage. So when it comes to a compromise between these parameters, it appears to us that silty clay loam is one of the best choice available, okay, to consider when you plan to plant if you plan to use the land for plantation. So looking for silty clay loam in the Terengganu area would be the best choice in terms of water management. Okay. So that's basically what I want to talk to you. So now I'm moving to other things that are slightly different. So now I'm going to talk about the other factors that I did not investigate in this study. For example, I mentioned to you earlier, evaporation is not investigated here. Rainfall effect not investigated. Different wetting and drying effect not investigated. Temperature effect due to solar radiation, soil bulk density, soil heterogeneity, and root water absorption. Those are factors that are not accounted in this study. And I actually did some study on the rainfall effect, but it's not complete. But I have some result to show to you. So this one is include the rainfall effect. So means the top boundary will sometimes wet, sometimes dry. So we have this kind of variable top boundary water influx. So as you know, Terengganu has a 2 seasons. One is wet and one is dry. So in the first half of the year is normally dry, and the second half of the year is normally wet. So you can see that the accumulation of water means this amount of water that actually enter the soil is initially constant. At the later part of the season, means the monsoon season, the water infiltration amount has shooted up. Okay, increases dramatically. And then if we observe the soil water content at different depths, we can actually tell how the water content actually changes with soil depth. You can see that the top surface, 0.01 meter, which is about 1 centimeter, 45 centimeter, 60 centimeter, and 120 centimeter. So you can see that at 1 centimeter, the soil moisture content actually varies according to the soil wetness. Okay, so it's wet, dry, wet, dry, wet again. So you have wet, dry, and wet again. So this kind of fluctuation is actually quite prominent at the soil surface. But if you go deeper into the soil, this fluctuation is less prominent. So this is actually more or less same as the temperature effect. Of course, we did not talk about temperature effect. So this temperature effect is also more influence on the surface rather than the soil depth. So apparently we are seeing the same thing on the rainfall effect. So increasing rainfall intensity increase cumulative water infiltration into the soil. Deeper the soil is less affected by rainfall variation. So you can see that at deeper depth, so the less fluctuations options. So you can see this green color is at the surface. You see even at the later time, the fluctuation is still larger compared to the different depths. Okay. Okay, so the limitation of water flow equation. So Bicara equation has some limitation. So it does not include vapor flow. It also did not account for the heat flux. So no temperature variation are included in this study. Bicara equation can give you water distribution. So you can see just now, you can see that this kind of water distribution in the soil. But if you include the water and heat equation into the Bicara equation, you'll get water distribution as well as temperature distribution in the soil. So you can actually know how it actually changes in the soil depth. So what is the importance of soil water content and temperature studies? They are important in agriculture, for example, biological activity, seed germination, plant growth. In fact, there's a study being conducted. They show that without providing water, you only provide vapor. So the means the air is actually wet. It's high in the relative humidity. So in this way, the seed will also germinate. Okay, so So it is important in agriculture. So vapor flow is important, not just water flow. And of course, the effect of temperature is also important. So these are important for irrigation. Also, soil salinization. If you provide too much what I call fertilizer, you could end up with a soil salinization effect. So in engineering application, for example, landfill management, nuclear waste repository, heat dissipation, underground power cable. Sometimes in a developed country, they got this underground heating. So this is also important. All right, vapor intrusion into a building basement. For example, if you maybe in Malaysia is not so frequent, only in commercial building. Most of the building in a sometimes in a developed country, they used to have this basement, right? So vapor intrusion is important. For example, this we call radiation, right? So here's I show you just a peek into the rigid equation that has been extended into water vapor and the heat flow equation. So rigid equation just now I showed you can be extended into this form. So basically here is referring to the mass conservation equation. So you have a mass conservation and also the heat conservation equation. Right, so you have this DTV. DTV is actually a term, particularly I highlighted here, is thermal diffusivity for vapor, and then the flux, the driving force is actually based on temperature gradient, also the water content gradient, and also the gravitational force. Same goes with the heat transport equation. We also have temperature gradient, also have a water content gradient as well as a gravitational force in play. Okay. So same, you want to solve this kind of equation, you have to solve it. You can use finite difference method. And similarly, you code it in a programming language, for example, Fortran, C++, R. Okay. So does our mass and heat equation complete? The answer is no. They are not complete. There are many things that we do not know. Just now I highlight the term thermal diffusivity for vapor. So there's a term called vapor enhancement factor. So this factor is not fully understood yet in the scientific world. This problem has been around for 60, 70 years. So nobody know what's the solution to this problem. Even though there are people are using the PDE, right? So a sudden decline in the waterfront during drying at the drying stage. So this kind of effect also present in the soil. It's some kind of mechanism that suddenly it suddenly, like when the soil becomes too dry, the water content suddenly drop drastically. Okay, so these are the things that are not yet included into the equation, and the equation does not include solute transport. So we talk about nutrient stuff like that. Okay, a saline thing. Uh, this water, the water vapor and heat flow can actually include the effects of temperature. Temperature and vapor, so that it becomes much accurate, and also include the solute transport equation. So your PDE will become longer, more complex to actually solve. And it does not include the dual porosity effect. So imagine that in the soil, you have one porosity that's a conduit that allow water to flow in and flow up, and then we have another porosity that's stagnant most of the time. So they are not involved in the water flow. They just stay stagnant. It's like a pocket, pocket. You just store the water, and the water inside you store does not move. So you have a dual porosity effect, as well as the soil bulk density changes. Okay, that's not accounted for. Of course, my current research already been shared by Dr. Rosali initially. So I don't think I need to go deep on that. So basically, what I'm working on is this mass and heat transport equation. I'm working on vapor buoyancy, and also working on the measurement instrument to capture vapor buoyancy. And then these are the funded research. I also have unfunded research, for example, working with the DOA. So it's more like corporate social responsibility. I just do it for free to DOA. So I'm helping them to solve clay soil problem in paddy field, as well as water management in the sandy soil, because Terengganu, we're near to the beach. We have lots of sandy soil. So we're trying to solve this problem, how to make the soil more productive in agriculture. So here's an example photo where I go to the site, actually requested a small area of land. So if let's say you're interested to study natural processes about soil, you can actually go to the meteorological department that close to you, request for a piece of land, install some sensors, and do some monitoring over time. And you can complement your data with some data available from them. because they're measuring this relative humidity, wind speed, temperature, solar radiation, things like that. So those data you can actually purchase from them and then use in your study. So that's all I have to share with you today. So I hope you enjoy the talk, and I'm looking forward for potential collaboration. And in fact, there are some students here. If you are interested to further study, for example, master or PhD degree, you are welcome to come and approach me and talk about it. Here I provide my full name, my field of study, and also there's my email address. So I'm looking forward for future connections. All right, so thank you very much for me. So I should return.
Okay, thank you, Dr. Sani, for the broad sharing on the soil and water topic just now. So I believe we have lots to learn from today's sharing, especially those who are from the background of soil physics and related fields. So right now I would like to open the Q&A session or any additional inputs from the audience, including the staffs and also the students that joining us today.
Good morning, Dr. Sani.
Yes, good morning.
I'm Siti Kamaria.
Yes.
I also doing some research on soil properties
Yes.
for pineapple plantation.
Yes.
But currently I'm not doing the water retention and infiltration studies. Maybe after this I can contact you to study more about water infiltration. And I want to ask something. How you do the infiltration test in whether at site or at lab for infiltration?
Yeah. So basically, there's a what you call double ring method. There's a
Double ring method.
Yeah, you can do that double ring method. Actually, I have not done that before because when I give you a brief history of my work. When I was in Japan, um, the professor gave me the problem to solve. So basically, it's a vapor enhancement factor. Just now I talked about that briefly. So I spent a lot of time on this equation and computer simulation code, stuff like that, and think about the theory mechanisms, how to actually solve this problem. And I also have some time touch with some laboratory work, but not much. So when it comes to the study of water infiltration, actually I should know about it, but I did not spend time on that. But we can work on that. I have the model, can actually do simulation on that. So I have a code that code this Richard equation. Richard equation can actually conduct simulation of water infiltration to the soil, and we can actually do a simulation based on different soil types. So all you need to do is you need to know your percentage of sand, percentage of clay, percentage of silt, and from there we can determine the soil textures. So from the soil textures, we can actually infer the water characteristic curve, and then we will get something useful out of it. And then with that information also, we can actually do water infiltration study, like what I showed you just now. So the information I provide you just now is based on the software, based on the source code that I developed and conduct the simulation. Of course, the most traditional way, people like hydrologists, when they want to figure out the infiltration, they normally take a double ring, they put on the side and they fill it with water and see and check the decline of the water with time, and then they predict the water infiltration rate. So if you can purchase that double ring, you can also make the double ring by yourself. If you want further information about this water infiltration using field work, like I show to you, if you want to work together on this water infiltration study, I can also work with you on that. So looking forward to have further discussion on that topic.
Okay, thank you, Doctor. I also have one more question. Doing the soil water test for the field capacity, permatan melting point, and available water, did you use any plants or prop in the experiment, or just using the type of soil?
Yeah. So basically, what I showed you this morning is basically we use these what I call management tools that we can actually predict the permanent melting point, this the field capacity soil water content by using this water retention curve. So in Malaysia, we are not actually in depth about this what I call techniques or this method, because UPM last time they used to be an agricultural university, and then they move out, they become University Petroleum Malaysia. So a lot of agriculture technology progress, I don't think we are actually on par with the progress in the United States and in Japan. When I was in Japan, they are very much still heavily invest in agriculture field. So, for example, soil physics for them is a very old field, soil biology and soil chemistry as well. And they look at environmental engineering, those as an emerging field. So for them, engineering, for example, environmental engineering, those are very new for them. A lot of science already been discovered in the agricultural field. So because these all the years of development, so they are in soil physics, they are actually able to come up with a technique that you don't have to actually go to the field. You don't have to put the plant in the soil to estimate the field capacity as well as the permanent wetting point. So all this estimation is solely based on the data that already been captured, because for them, if you know the percentage of sand, percentage of silt, percentage of clay, you can predict the soil texture. So from the soil textures, they already have in place the equation that govern the soil water content relate to the soil metric suction or the soil pressure. So from there, they know that the field capacity is actually at field capacity is at negative 330 centimeter, and the permanent wetting point is at negative 15,000 centimeter. So they use the equation they have. They predict the soil water content at field capacity and the soil water content at permanent wetting point. So from there, they know in hand what they are going to what are they going to expect. Of course, this estimation is not as accurate as if we go to the field and actually conduct the laboratory. So some tweak and calibration might be needed. So yeah, so your to answer your question, so when they predict the field capacity and the permanent wetting point, they do not have a plant in the soil when they do that.
Okay, thank you, Doctor.
Yeah.
And then you more going to in the simulation and using sensor for the soil moisture and soil moisture measurement for the soil sensor. Using
Yeah.
soil sensor, you
Yeah.
develop yourself.
When I was in Japan, my professor is actually into TDR, time domain refractometry. So this is the best sensors you could get in the market. But the sensors, you need to create this pulse, right? You need to have this kind of tectronic this instrument, very huge. You need to provide power supply. I actually know how to develop the sensors. I developed the I know how to fabricate the sensor, the TDR sensors. And inside the needle, there are 3 needles inside it. Sometimes they prepare in 2 needles, depends on the development. 3 needles. The needles is used to accept the incoming pulse and so send back the incoming pulse. And then the inside the sensors, they have thermocouple. In soil physics, they use type T thermocouple. So they use a copper with constantine, something like that. I forget the name. So they combine this cable, 2 wire together, and the quality of the wire has to be very, very good, pure copper and pure constant. Then you insert into the needles, and then you fabricate the casing to hold the needles, and then you connect the wire to the tectronic, and then you need to provide power supply, things like that. So I did that when I was in Japan, but unfortunately, when I come back, I have no time to pursue that. So I still have the skill to do that, but I tell you what, if you want to do that, it's very, very time consuming, and you can actually spend a master degree or PhD just to do the work on the sensors itself. So my suggestion is the best way to actually benefit to work on the science is to use the commercial sensors. That will save a lot of time, so you don't have to waste too much time on the sensor development, because it's more on the electronic and instrumentation work. So one sensor costs you about 1,500, 1,000, depending on the kind of brand you're going to use it. You want to use it, yeah. So these are the price I have to pay. Otherwise, actually, I have the sensor. If you allow me for a second, I show you the sensors.
Okay.
Yep. So, can you see me? Yeah, you can see me, right?
Yeah.
Yeah, I'll show you the sensors that I developed back in Japan. This is how it looks like. Yeah.
Oh.
Yeah, that's how it looks like. So you have a needle, you have a casing. So this casing, we have to ask because when I was in Japan, they have a department that can actually fabricate this casing, and then inside the casing we have to put this epoxy to solidify the thing. You see, there's a lot of cable. Okay, so inside here we have a temperature sensor as well as this TDR, this cable for TDR, and it also needs to have a certain resistance. Like we call it, I think 50 ohms, something like that. So you have to solve this kind of thing, and yeah, and you need to get the pure material like copper, stuff like that. Yeah. It's not an easy job, and then I actually go through the whole process. It's just that I don't have time to pursue everything. You see, I developed the source code, so it also take a lot of time.
Oh.
So, and also I also have to use sensors like relative humidity sensors because I work on vapor. Yeah, a lot of things. So end up I give up. I also spend some time on this Arduino sensor, the water resistivity sensors. I also give up on that. So it's just too much time. If you are interested in Arduino, you can Arduino, you can use a resistivity sensor, right? As one time I accommodate up to 6 sensors, and then you even have time tracking. We can track the time. We only have data logger. We can actually data log the measurement from the sensor. So I have the whole package developed last time, but I also give up just that there's no time. So remember, let's say for example, you work on the plantation, you want to work on the nanas, right? Nanas.
Yeah, nanas.
You want to focus on the water management thing, so you want to focus on the science and managing the water. So, but if you spend too much time on the sensors, stuff like that, then you have less time available for you to work on your water management on the nanas thing. So that's what I realized eventually, because once you have family, children, this whole thing just have to give up a portion of your activity here.
I think one of our lecturers also doing develop the soil sensor.
Yeah. So is it something like TDR or capacity?
Not sure because another lecturer doing that.
Maybe Dr. Firdaus want to share something with us today?
Ada?
Dr. Firdaus ada tak kat sini?
Ada.
Dr. Firdaus? Yeah, okay. Is there any other questions or any maybe you want to share any thoughts with Dr. Sani today?
Okay, thank you Dr. Sani for the explanation and answer.
Yeah, thank you for asking. Otherwise, I almost forgotten I actually worked on this sensor thing last time. Yeah, because actually on my table for I think 3 years already, it's not moving. So today you mentioned I just move it and show it to people. It's really no time. Yeah, when it comes to when it comes back, when I was a student back there, I can work on it. I thought I want to work on it, but just no time. Yeah, it's impossible.
Thanks, Puan Kam, for the questions and the sharings. Lee Kwilu, is there any questions?
Yes, I have question. Good morning, doctor. I'm Lee Kwilu. I want to ask one question is there have any difference if I use solar soils to replace the soil and using those methods, is it suitable?
If you use soil, I'm not sure what kind of soil you're going to use. Maybe you're using if this method is only applicable for if you can determine the percentage of silt, percentage of sand, percentage of clay. So you need to have these 3 components in play. then only you can predict the soil water characteristic curve, right? So then you can predict the permanent wetting point and stuff like that. Take for example, I'm not sure exactly soil, which one you're referring to. Take for
Solar
example,
soils. Sorry for interrupt. The solar soils that I'm using is like the coil pit and the rye husk ash.
yeah. So if that's the case, it's going to be different. Yeah, it's going to be different because if you use a cocoa pit, one of the reasons you use a cocoa pit is you want to increase the air volume space, and then you compensate that by using what I call organic, they call that organic soil. Yeah, so you mix a few different things inside, and then you modify that. So I think that one is not applicable. But the good thing is this. Um, this characteristic curve you can easily develop as long as you have sensors. So right, so if you have sensors, there are few sensors around. One is a tensiometer. Tensiometer measuring the soil metric suction. The one that tensiometer is able to do that, and the other one is water potential sensor. That one is a bit hard because it's more complicated. So tensiometer is something that you can look forward to measure. So if you use tensiometer, that also means that you need to weight your soil when it's dry and compared to when it's wet, so you know how much water is in the soil. Yeah. Yeah. So you need sensors, tensiometer, and then you need to do a manual weighing without water and with water. So these are things that you need to deal with.
Okay, understand.
Mm.
Thank you, Doctor.
Right.
Okay, so any other questions before we stop the session today? And maybe close with another questions, the last one from the audience. Ada lagi tak apa siapa? Okay, jika tidak ada, so maybe Dr. Sani, we will surely to have another outside discussion. Okay, we will surely have to have another outside discussion for potential collaborations integrating between the soil physics and soil chemistry one fine day, where we could figure out something to be studied later. So hopefully I can go back to UMT then once the MCO in COVID has been cleared to join your interesting fieldwork someday maybe.
Yeah, thank you very much.
So it is great to talk to you today after so long and exchange ideas and thoughts with my current peers in UNIMAP. So thank you again, Dr. Sani, for the sharings. And thank you for all the audience, including the staffs and students for joining us on board today. Thank you and very good day to all of you.
Okay.
You're welcome. Thank you very much for joining.
Thank you very much. See you
Thank you,
guys.
Doctor.
Thank you, Doctor. Bye.
Ya, dia dah keluar.